Okay. Okay, good afternoon. Ready for the next session? Yeah. Okay. So, so now you are somewhat familiar with the material science concepts, right? Now let's dive into the magnetic materials, which are part of functional materials, one type of functional materials, right? So I'll be talking about some of the fundamentals of magnetic materials so that you can make use of these functional materials to solve any engineering challenges that you have. Okay, so if you have studied Callister, a lot of the slides come from Callister, but um, I go beyond the slides. Um, so not just theoretical part, but also some of the things that can only be explained by somebody who has experience in the field. Okay, so what we are going to do is we look at how we can generate magnetic field and what are different type of magnetic materials and what are the important magnetic properties and how does the phenomena originate, yeah, and and then what are permanent magnets, and then what is we look at some of the applications. Okay, in the applications we look at magnetic memory, which is your hard disk drives, and other applications, how magnetic materials are used. um, so with that, so now who can tell me how do you generate magnetic field? Where do you see magnetic fields? Or how to generate magnetic field? Where is magnetic field? What is it? There is a simple high school explanation, right? Any current carrying conductor produces a magnetic field, right? So charge in motion creates a magnetic field, right? So any wires that carry current will have magnetic field around them. Okay, so currents, that is charge in motion, creates magnetic field. So it's very easy to create magnetic field if that is the case, right? So now, but the strength of the magnetic field is what that matters, and how do you make use of it, and what is the other way? Okay, charge in motion is one thing, but there are other ways to generate magnetic field. How do you generate, or where else do you experience magnetic field apart from charge in motion, apart from current? You all use it. Permanent magnets, right? A permanent magnet has a magnetic field around it. Okay, so now let's look at how to generate magnetic field. So we know charge in motion generates a magnetic field. So the important parameter then is the charge in motion, which determines the magnetic field. So that is current. Current determines the magnetic field. But current, if it just goes in one wire, it's not most efficient way to generate magnetic field. So what do, you increase the surface area of the, or the length of the wire by making it several rounds. So that's a solenoid. And again, it's high school physics. So in a solenoid, you make several rounds close to each other, and it's, some of the solenoids are very compact, not just one layer, several, sometimes it can be hundreds of layers, depending on how strong you want magnetic field. So because the strength of the magnetic field represented by H. Okay, so remember that H is the magnetic field, and B naught, or B, is the flux density. Just keep that in mind. We will come back to it. Okay. So now B in air is just B naught. Okay, or B0. So the magnetic field equals N multiplied by I divided by L. N uh, is the total number of turns, and I is the current. So divided by L, the length of the solenoid, will give you the magnetic field. Okay, so it's a very simple equation. You can, if you want higher magnetic field, increase the number of turns or increase the current, right? So simple. Now let's come back to the B parameter, that is the flux density. Okay, so B is normally generated within a material. So if you go inside this magnetic field or go close to the magnetic field, any material, so if you are a person, it's of course our tissue, how it responds to the magnetic field. It's like equivalent of voltage, right? You apply a voltage, what happens? Or a voltage to any insulator, current doesn't flow. But similarly, if you apply a magnetic field to a non-magnetic material, nothing happens, right? But if you apply a magnetic field to a magnetic material, which is ferromagnetic or paramagnetic or ferrimagnetic or diamagnetic, these are different types of materials which we'll cover, then the B, which is like the current, right? So how current is important in generating the magnetic field? Likewise, B is important in generating the after effects of the magnetic field, which is induction heating or generating torque in motors. So that depends on B, which means you have to choose the right material. If you choose the material that doesn't respond to magnetic field, it's useless. You can't get heating, you can't get torque, right? So B is the material response, H is the field that you generate. Is that clear? So now you put a iron core there, so it will have certain B, that is the magnetic flux density, and that depends on the permeability of that material. Okay, just like resistivity determines the current when you apply a voltage, permeability determines B when you apply a magnetic field. Okay, it's just, straightforward. And just like how current heats or current does different things, B does different things, and you need to maximize B. Okay, and mu is the permeability, but usually we represent, it's a very odd quantity, so we usually divide it by permeability of the vacuum or air to get relative permeability. Now relative permeability is like real numbers. Okay, so you get 5, 10, 5.5, whatever it is, and you can go all the way from 1 to million. Okay, so that's relative. Higher the relative permeability, higher will be the B for any applied. You apply small field, high B. High B means high work you can get out of it. Okay, so, and there is another term that is normally magnetization is similar to B, but it's a different parameter. Again, magnetization is materials response. It is similar to B, but the quantity is slightly different because it is dependent on chi, but both are related. I'll show you how. So this Greek letter chi is called susceptibility. Permeability, susceptibility, they're similar, right? So they're like the resistance or resistivity. They're like resistivity of a material. And susceptibility is dimensionless, so is the relative permeability, but permeability, it has a dimension. Okay, so now, so magnetization is chi h, B is mu h, But if you want B in terms of H and M, it's mu naught H plus mu naught M. So you see here, B depends on both the applied magnetic field as well as the magnetization. Okay. So now you can use a different version of the same thing. Instead of 2 mu naughts, you can have chi as another parameter. And so permeability of vacuum, you see it's so small quantity, and it is Henry per meter. Okay. So all you need to know is here B is the parameter that you need to maximize. H is the field you apply with the current or by other source. And M is an intrinsic property of a material as well. Okay. So now if you look at different materials, so for materials which have susceptibility lower than 0, susceptibility can be lower than 0, but permeability is always above 1. Okay. Because vacuum's permeability is 0, 1. This one, relative permeability is permeability of vacuum divided by the permeability of a material divided by the permeability of the vacuum, right? So now, so for high magnetic materials or ferromagnets, the chi value is greater than 0, vacuum chi is 0, and some materials have chi less than 0. Okay. So these are three different materials. Does anyone know which are these materials? Chi less than 0, susceptibility, negative susceptibility. What kind of material has negative susceptibility? Diamagnets. Okay. Okay. So actually, I wish I had a board. So this is not a good picture. I think I have another slide later when I'm talking about different type of materials. It's better to not to look at chi. It's better to look at permeability. Okay. Sorry. So I was saying, yeah, that is less than 0. But yeah. So so yeah, if you can bring, but yeah, I may not use later on, but it's better to have it. Yeah. So here susceptibility, when susceptibility is lower than 0, that is negative, your B is still positive. Okay. But if you, this is good representation, but if you do M versus H for the same materials, what happens is this vacuum will have 0 B, and negative susceptibility material will show negative B. Okay. So that means whatever effect you get for ferromagnetic materials, you get opposite effects when you use a diamagnetic material, if you look at magnetization. Okay. So, but again, we for simplicity or for use cases, for applications, you don't need to go that deep. All you need to understand is B and M are related. If somebody gives you M, you can determine B by using susceptibility as well as permeability, and H is your variable. So for any given field, you know what is M or B. Okay. So now we talked about how the um, materials are magnetic, or how the magnetic field is generated, right? Charge in motion creates a magnetic field. That means, so what, every material should have magnetic field, right? Because every material has electrons. Electrons have charges, right? So all electrons, when they spin, they're in motion. So electrons don't just stay stagnant, right? They have two motions. Electrons, one, they have orbital motion that go around the nucleus, or electrons, or not or, and electrons have spins. And is it, you can just put it there, right? Yeah, that's fine. Yeah. So so this is, here mu r is greater than 1, which is not just greater than 1, very large compared to 1. Okay, and here mu r is greater than 1. Here mu r is smaller than 1. Actually smaller than, yeah, for diamagnetic materials. Okay, so I don't know, my handwriting is not that clear, but this is ferromagnetic material, paramagnetic material, diamagnetic material. Okay, so when diamagnetic, you apply magnetic field on diamagnetic materials, this show negative magnetization. Okay, and paramagnetic materials will show higher and higher magnetization as you apply magnetic. So you, right? So here for diamagnet, you are making the, but in the, what happens in B is, because B equals H plus M, so although M might be negative, because M is negative, but because you're adding H and you're increasing H, so your B C is always positive. Does that make sense? So if you have very high mu r, so for any small change in magnetic field, the magnetization, or B, increases rapidly. That means you can make use of this material with, by applying small magnetic field, you can generate a large torque or large heating. Does that make sense? Yeah. So now what is the origin? So charge in motion, right? So two motions for an electron. One spin, which is this one, and the other one orbital. They go around. So electrons not just go around, it's just like Earth, spins on its own axis and then goes around, right? So electrons have magnetic field due to spin as well as orbital motion, right? So, but the orbital motion contribution is not that much, whereas spin has the highest contribution to the magnetic field. Okay, so the electron's spin motion creates much higher magnetic field than the orbital motion, so spins contribute the highest magnetic field. However, materials, you know Pauli's exclusive principle, right? In a single shell, electrons don't have two spins, they always have opposite spins. So in one orbital, when there are two electrons, for example, s orbital has two electrons, the spins are always opposite. So what happens? Magnetic field cancels out. So when you write your electron configuration of your material, you will have some electrons unpaired spins, right? So those ones will have high magnetic field. So that means you have to identify in the periodic table which elements have unpaired spins, because that will have more magnetic field. If they are paired, they cancel out, right? So the story is not over yet, but the problem is, again, individual elements don't occur as individual atoms, right? Atoms combine, and the way they combine is, again, the spins cancel out. Okay, when the atoms form molecules, the spins cancel out. Okay, it's very difficult to have unpaired spins, because unpaired spins meaning it is carrying energy. Any material that carries energy is in a higher energy state, right? So they always want to come back to ground level, which is low energy state. That is more stable. So that's why a lot of the elements have very few unpaired spins, magnetic spins. So there might be unpaired electrons, but they cancel out. So the resultant spins are always. So instead of B, again, as I said, this is diamagnetic, right? So here you can see higher effect if you measure M, because M will show negative, right? Here, because you are measuring B always have M plus H, right? H term, so you are always adding H. So your M, although M is negative, but H is positive, so it shows positive sign, okay? So whereas H here is, this is the axis here. Maybe let me neatly write it so that you can see. I'll just write para to understand paramagnetic. Dia and ferro. Okay. So some of the diamagnetic materials are copper, gold, I think silver, silver, silicon, zinc. Water is also diamagnetic. Do you know the levitating frog? There's one type of frog, you can put it on a very high magnetic field, it levitates because it is repelled by the magnetic field. That's a cool experiment. And then vacuum, of course, zero. So these are diamagnetic materials, though they repel the flux lines, okay? But the repelling force is not that great, because the susceptibility is not a big parameter, okay? And then there are paramagnetic materials whose magnetization of B increases, but marginally, okay? So which means their susceptibility is somewhat small, or even if you look at their mu r, that is also small. And these materials are aluminum, molybdenum, sodium, titanium, zirconium, and so on and so forth. Okay, whereas ferromagnetic materials or ferrimagnetic materials are ferrite, which is Fe3O4, nickel ferrite, which is Fe2O4, cobalt, nickel, gadolinium, Fe is also ferromagnetic. And don't worry too much about ferri and ferro. There is slight difference. Ferro has the highest, ferri has little lower, but both are high magnetic materials. Okay, or magnetic materials with high permeability or susceptibility. Okay, these are different types of magnetic materials. So that means if you want to make use of the functional part of the magnetic material or get work done by a magnetic material, you need to focus on ferromagnetic materials. You can, of course, do paramagnetic as well, but the work done, the torque will be small, heating will be small, whereas it will be very high in ferromagnetic materials. Okay? So is that clear? Now, in a diamagnet, so if you don't apply any field, the spins are, this is what you see. There is no effect from individual spins or individual electrons. But if you apply a field in this direction, we are applying field in this direction, the red arrow, right? What happens is in diamagnetic field, the spins oppose the applied magnetic field. If the magnetic field is applied in one direction, the spins will orient in opposite direction. If there is no magnetic field, they don't orient, they don't have a direction. Okay, they're just spinning around. But if you apply a magnetic field, they align themselves to oppose the magnetic field, applied magnetic field. That's diamagnetic field. Okay, so that's why the magnetization will be negative for these materials when you apply a magnetic field. It will be 0 at no applied magnetic field, but if you apply magnetic field, the magnetization becomes negative. In case of paramagnet, they have some spontaneous randomly oriented spins, but when you apply a magnetic field, they orient in the direction of the magnetic field, but not completely. They orient such that most of them cancel, but there is a little net effect. So for example, this is this and this oppose each other, right? So the net effect is small. So the total magnetization, if you take here, because of the changes in the directions, you get the net vector sum here will be smaller. Whereas for ferromagnet, the spins are randomly oriented when you don't apply any magnetic field, and when you apply magnetic field, they all orient in the direction of the magnetic field, and you get a very high net magnetic field. Okay, so is that clear? This is how, this is all to do with electron spin. Okay, we completely ignore orbital's motion because it's very small. Right, so if you look at different type of materials, diamagnetism, these are the examples. So here is M, and it's not B, but so here is, this shows M. See, you see negative magnetization for diamagnetic materials. And for paramagnet, you have small. For ferromagnet, you have very high sudden jump, and then it saturates. This is the key hallmark of ferromagnetic materials. They have really high magnetization or magnetic flux density, but then after a while they saturate. Whereas paramagnets don't saturate at all, they keep going. Okay, so these are the two hallmarks. If you want to know whether it's a paramagnet or a ferromagnet, you just do a magnetization measurement by applying magnetic field and measuring magnetization, and if it starts to saturate, that means it's a ferromagnet. But if it's not saturating, then it's a paramagnet. Then there is antiferromagnet, which is another class of materials, and that shows response similar to paramagnet. Then there is ferromagnet, which is always consider this one, right? Because it has highest permeability, highest saturation magnetization, or highest magnetization, and you need to apply only small field to make them highly magnetic. So how many magnetic, okay, I said that it's easy spin, wherever unpaired spins are there should give a magnetic material, right? So how many magnetic ferromagnetic elements are there in the periodic table? Oh, you can see there. We have 118 elements, right? Oh, not all 118 are shown here. Okay, what? 3? Yeah, 104 should come here, and up to 118. So there are 118 elements, but most of them are useless because they only live for a fraction of a second, which is microsecond. All these above 92, all these are man-made materials that are stable only for microsecond, right? So those are, so that's why you don't know what is there, whether they're in liquid phase, solid phase, or what. So coming back to the question, how many elements are there that are ferromagnetic? Sorry? 4, somebody say? So remember, ferromagnet is the highest magnetic material, right? So there is iron. So chromium is, it's not ferromagnet, it's antiferromagnet, meaning it's similar to paramagnet. Okay, it's not, I wouldn't consider this as a ferromagnet, but if you know how to tune the spins in a lattice structure, in a crystal structure, you can make it a ferromagnet. Okay, so all you need to do is change the spin direction of some individual atoms, then you can make. So naturally occurring ferromagnets, iron, cobalt, nickel. There is also gadolinium, but not in India. In India, gadolinium is not a ferromagnet. Do you know what does that mean? Its Curie temperature is 292 Kelvin. So which is about 20 degrees. And 20 degrees, most of the time in India, it's about 20 degrees. And about 20 degrees, it's not a ferromagnet, it's a paramagnet. Okay? So I wouldn't consider this. So only 3 in warmer countries, and gadolinium maybe in colder countries, not in summer. Okay? So gadolinium has a transition temperature close to room temperature. So it becomes paramagnet. So what does that mean? Why some materials from paramagnet to ferromagnet? That's a big change, right? And just by changing few degrees temperature, some material can become ferromagnet versus paramagnet. So, but as I said, chromium, just the way the atoms are arranged, it's antiferromagnetic. There are opposing spins within one lattice. Okay, it's not like there are two different molecules that's coming and canceling the spin. It's within a crystal structure, there is misalignment. That could be changed. So that's why a lot of chromium materials can be, chromium compounds can become ferromagnetic. Just if you mix them in a right proportion, then you have right alignment. Okay, so these are the only ferromagnetic materials that exist. However, these ones, the paramagnets, will have a Curie temperature. For example, gadolinium becomes paramagnet about 292 Kelvin, which is about 20 degrees centigrade. That means the other paramagnets will also have Curie temperature, right? So that means these are all paramagnets. Presbymium, promethium, not europium. Yeah, these two. And yeah, even these are all paramagnet. Palladium, rhodium, titanium. That means they have a Curie temperature. At that temperature, all the spins will realign and they can become ferromagnet, right? So if it's a paramagnet, that means they can also become ferromagnet at Curie temperature. Because all ferromagnets, these will become paramagnet at one temperature called Curie temperature. It's the temperature at which all ferromagnets lose their magnetic property. Okay, so now let's look at how the spins in the material change as you apply magnetic field. So if you start applying magnetic field, here are the different spins oriented at different directions. At zero applied magnetic field, there's nothing. Even for ferromagnetic materials, if there is no magnetic field applied, they don't show any magnetization or B. Okay, so it's zero. As you start to apply magnetic field, if it's a ferromagnet, the magnetization or B goes up rapidly, right? How does that happen? So there are all these spins. They start to reorient. So look at this one. This is growing. See this? This starts to grow because the magnetic field is that side, right? Which is, this direction is domain. We call it domain. These are all domains. These are artificial regions, okay? If you look under microscope, you don't see a domain as such, okay? Just like grains are visible. You take a really good microscope and you can see grains, right? In a polycrystalline sample, you see grains. But if you take a magnetic material, you can't see domains. These are domains. Okay, each domain has a specific spin direction. These are virtual regions, okay? So now you see this is growing. Actually, this is growing as well. So eventually you will get all the domains will align in one direction. Okay, domain is a artificial construct that we use in order to explain how the magnetization, all the spins orient in one direction. Okay, so now why is that domains? Why should domains become one? Not, or if at high magnetic field there's only one domain, why can't materials exist as one domain? Why should it exist as multiple domains? Right? So this is the ground state. Materials like to have multiple domains because if you have only one domain, look at the magnetostatic energy. The magnetostatic energy, again, I don't want to go too deep. The Faraday's law, which is curl, the magnetic fields are always closed loops. Okay, the flux lines always close. If it is one domain, they have to close in a much bigger area. Okay, so the magnetostatic energy to maintain this domain is high. because the flux lines have to be large. Whereas if they are in multiple domains, they can close the loops within short distance. Okay, so the magnetostatic energy there is small. That's why they tend to stay in a multiple domain. They become one only when you apply a magnetic field. Does that make sense? So here is, let me see if this video works. It doesn't have audio, so that's fine. So remember, there is no such thing as physical domain. It's an artificial construct. Then you are asking, what is this image? Right? What is that we are seeing? We are basically seeing through a polarized lens. We reflect light, we direct light, and light reflects back. And the light will respond in a different direction to uh, different direction of the magnetic field. If the magnetic field is in one domain, in one direction, the light will have a different contrast. Not a lot of light will come back. Okay, so that's what creates this dark and light images, because we use a polarized light that will respond differently to different direction of the magnetic field. So, and the direction of the magnetic field is different in different domains. So whenever we see light, and that represent the domains. Okay, so you need to have a special technique to see the domains. And here is another one. And it's not easy. I have tried it. It's called Kerr microscopy. So you have to, and sometimes you see, so this, if you see this one, yeah, sometimes the domains are like this. Okay? Right, so now the another important thing in magnetic materials is hysteresis graph. Okay, hysteresis graph is how the magnetic fields behave when you apply magnetic field and take off the magnetic field. So if you apply magnetic field for ferromagnetic materials, B or M, doesn't matter. Okay, there's a small difference. So it will increase rapidly and then saturates, right? That is the hallmark of ferromagnetic materials. Now, if you remove the magnetic field, right, you increase the magnetic field, so the magnetization increase that way. Now you remove the magnetic field, the magnetization doesn't come back to zero. It comes back to a certain value. So this is called the remanence. And that not all the materials will have remanence. Okay, only some materials will have remanence. It is useful. We'll talk about that later. And now if you take the magnetic field in the opposite direction, you can make it zero. So here the B is zero, but you are at a negative magnetic field. Okay, now if you go further to the negative field, you go to the negative field, now the magnetization increases negative in the negative direction. Now you remove the negative field, go back here, it comes here, now go here, it comes. So this is called the hysteresis loop. Okay, so this is remanence magnetization or remanence B, and this is the coercivity or coercive field. That is how much field you need to apply to make the remanence go away, right? So that means you can, some magnetic materials, if you apply a magnetic field, meaning if you apply current near them, they saturate, and if you take the current off, they retain some magnetization. Okay, and to remove their magnetization, you have to apply some negative magnetic field. Okay, so that is the coercivity, how much negative magnetic field you need to apply to make it zero. This is the remanence, this is the saturation. Okay, so that is saturation magnetic, saturation magnetization is this one. I'll make it easier for you. A lot of the materials, this is H, this is, let's do M for simplicity. Okay, so that is MS, saturation magnetization. This is MR. Okay, it's also BS or BR. Okay, don't read it as MS by BS. Okay, so that is, then this is the, it's asymmetric, it should be symmetric. Okay, so this is HC, coercivity. Okay, so these three are very important parameters for any magnetic materials. So here is some magnetic materials will have very high remanence, some materials will have small remanence. Some materials will have very high coercivity, meaning you need to apply really large field in order to remove this magnetization. Okay, whereas in some material, a small negative field is enough to bring back the remanence to zero. Okay, so these are soft ferromagnetic materials, these are hard ferromagnetic materials, meaning they retain their magnetization. You need to really apply high coercive field in order to remove their magnetization. Whereas these are soft. Tiny amount of negative magnetic field will be enough to remove the magnetization here. Okay, so these are hard and that's soft. So the hard ones are called the permanent magnets. The soft ones are called the soft ferromagnetic materials, or they're used for applications such as motors, transformers, actuators, speakers, yeah, and inductors as well. So yeah, there are many applications of soft magnets and hard magnets. And of course, hard magnets are source of external magnetic field or external B for us. So here are different hard magnets. Has anybody bought a permanent magnet? Or has anybody ordered a permanent magnet? Yeah? So how did you decide the strength of it? Because their strength can vary, right? How did you choose the strength? People can sell you very weak ferromagnet or a hard magnet or a high strength magnet. How do you know? See, what is, there is a parameter that companies specify to denote the strength. So let's go back to the, so this is the remanence, right? That is the coercivity. And so every time you apply, it retains. So that is a retained energy in the magnetic material. So that's why they're hard magnet. So if you take the remanence and multiply with the coercivity field, you get what is called energy product. And higher the energy product, higher is the remanence and higher is the coercivity, stronger is the magnet. So that means you have a better permanent magnets. Though, so they are measured in terms of energy product. So it's the product of coercivity and remanence. And it's measured in mega-Gauss-Oersted or kilojoule per meter cube in SI unit. So the mega-Gauss-Oersted is nothing but N. Normally people sell magnets in N50, N45, N30, right? So that is nothing but this is the mega-Gauss-Oersted. So mega is 10 to the power 6, Gauss is the B, and Oersted is the field. Okay, and see, you can see nowadays there are 50. You can get N55, although if you go on eBay or Amazon and buy, they're usually N50 or N45. N55 is rare. So stronger the magnet, stronger is N or mega-Gauss-Oersted. Okay, so you see in olden days, the permanent magnets were KS steel, MK steel, alnico, samarium cobalt, and other versions of samarium cobalt, and then came neodymium iron boron. And neodymium iron boron was discovered in 1980s, and nothing has happened after that. These are all marginal increase in neodymium iron boron. No other material has been discovered that replaces neodymium iron boron. Okay, so those are really strong magnets. These magnets are so strong. If you take a 2 centimeter by 2 centimeter magnet, their attraction force is so. I'm talking about N50. Okay, you separate them by 5 centimeter. I'm talking about a cube of 2 centimeter by 2 centimeter by 2 centimeter. This big. Okay, separate them by 5 centimeters and leave them. They attract so hard that they will break, first of all, and when they break, you can see sparks coming out. They're that powerful. And people who work with N50 magnets, they will always have these skin pinch injuries because they always, and you get these skin tear because of those. So they're that powerful. And if you have this big permanent magnet of N50, you got to be very, very, very careful. We have 2 of them in our labs. They are set in one place. I only let senior graduate students to handle them. And once they're stuck, of course, when they get stuck, they will do some damage, either to themselves or to whatever in between. But once they're stuck, you need special apparatus to remove them. Okay, so they are very powerful magnets. And here are different type of, again, so kilojoule per meter cube is, you can convert it into N by dividing them by 8. Okay, so this is just 4 point something, 5 point something. So N5, that's not big. So here you get N45 magnets. How are they made? The permanent magnets, first they do the composition, chemical mixing, the chemistry. Then it's not a simple process. So it's a very expensive, high capital cost. So you can't just go and set up a factory to make a permanent magnet. You can if you have very high capital. So you need all these machines. Okay, so it's first you have to strip cast after you make the powder, hydrogen decrypitation, jet milling, aligning in a magnetic field. You have to align them, pressing them in a magnetic field, sintering, then annealing. So I think it's GBDP, meaning grain, I don't know, whatever it is, Machine coating is not, this is nothing but electroplating. Now, because magnets, they don't look that shiny. Then finally, you magnetize the material. You apply this large field to saturate them. Okay? Then they become a permanent magnet. You need really high negative field to unmagnetize them or remove their magnetization. Okay? Okay, so permanent magnets, they are a passive device for generating magnetic field, right? So you get perpetual energy from permanent magnets. They're not like batteries, right? Batteries, they after certain use they go away, but permanent magnets, they give you magnetic field permanent in, perpetually. So where does the energy come from? You can't have a perpetual machine. No, it doesn't. So are you saying that it comes out of saturation? No. So are we saying that they're perpetual machines? But we know that, fundamental physics tells us that perpetual machines do not exist. So where is the energy coming from? So you have to, if you apply small negative field, the power doesn't decrease. You still have that remanence magnetization that remains. It's like spring constant, okay? It's like we deposited that magnetic energy in the beginning, right? We created a spring. Now, anytime you push the spring, you have a repulsive force. Similarly, you have created a spin alignment, and because of the nature of the spins can't go back to their ground state. They're all stuck, in one direction. And there are so many atoms stuck in one direction, you get additive. And if you want to, it doesn't change. It's like spring. It has already, you deposited the energy and it's stuck there. If you want to make it zero, you have to bring all the spins back to ground state. Okay? So now, there is another important parameter called magnetocrystalline anisotropy. So basically, if you look at crystal structures, right, the magnetization, we are done with the permanent magnets. Now let's go back to just magnetization. So right, this is your yeah. So this is your C axis, B axis, A axis. Okay, it's actually small of a crystal structure. Okay, so now if you apply magnetic field in this direction along A axis, you get like that. if you apply in C axis, like that, and you apply in B axis, they all attain saturation, MS, but their slope changes. And slope meaning, that means if you apply a small magnetic field, this has very low magnetization compared to this one. Look at this. This is already saturation, right? For this field, say, let's say 1 kiloasted. For 1 kiloasted, in direction C, you are very small magnetization, whereas direction A, so let's say this is A, this is B, this is C, right? B is intermediate, A looks like D. Okay, A has very high magnetization. So this is directionality, right? So that is what is called anisotropy. And this comes because of the crystalline nature. This is called magnetocrystalline anisotropy. And different crystals, if it's hexagon always have easy axis. This is easy axis. Hexagon longest axis is always easy axis. And it has much higher magnetocrystalline anisotropy compared to the base planes. Okay, so that means if you want very high relative permeability, you choose a hexagonal structure, crystal structure, and align the long axis of the hexagon, and that will be very high relative permeability. Okay, that means you apply very small field in this direction and you get high magnetization. So that is magnetocrystalline anisotropy, and that's what a lot of electrical steels use. In electrical steels, they texture the steel such that the A axis align in certain specific direction, and you get what am I supposed to finish? What time did I start? 4 to 5:30, right? Okay, I have 10 more minutes. So this is magnetocrystalline anisotropy, and meaning you engineer materials such that you get highest property, which is in our case highest permeability in the direction that we want, right? This is another processing technique wherein we can design materials that have better performance in a specific direction. So magnetocrystalline anisotropy also determines your coercivity. So this coercive field is higher for materials with high magnetocrystalline anisotropy. So that means we can make use of this texturing. I mean, if we can grow single crystal, that's perfect, right? But we know that growing single crystal is very difficult. So what you do instead is the crystals might form, but you somehow make the crystals to orient in one direction. So you still have crystals or the grains, but you make them orient in a way that is, you can use certain rolling techniques, or you can cool it. When you're cooling it, you apply magnetic field, external magnetic field, so the easy axis aligns to the field direction. Now all the grains that are formed have direction oriented to the applied magnetic field, which is, you control the lattice directions of all the crystals, all the grains in one direction. You did not get a single crystal, but you made all grains orient in one direction, right? So that is called magnetic annealing, which is a process that is used to align the grains. So now there are so many applications for permanent magnets. Permanent magnets is a very big industry. India lags behind in permanent magnet manufacturing. Do you know which country is the leader in permanent magnets? China. You know what's their share? How much is their share of the permanent magnet across the world? 95. Okay, they control the permanent magnets. Any permanent magnet you see, it's invariably has come from China. Okay, because they mastered the way to purify rare earths, and all permanent magnets are neodymium iron boron, right? So neodymium iron boron, of course, US is the leader. US invented it. US refined it, identified the process. Everything done in US, but the mining of neodymium, samarium, and in neodymium iron boron, there are small quantities of dysprosium as well. All those rare earth metals, they have similar magnetic properties and similar chemical properties as well. So it's very difficult to extract them. And the process is very intensive, and a lot of rare earths, because they are closer to the actinides in the periodic table, actinides are radioactive materials, right? Uranium, all of them in polonium, they come under actinides. So you find some radioactive materials. So mining them is somewhat not a safe process. So it became very expensive in the US to mine them because of the safety precautions that were put in place by the government. So China, they all shipped all their ore to China, and China also had large amount of ore. They started buying from China since 1970s, and then China dominated because it's much cheaper to buy from China than make it in the US or Europe. And in India, we don't have that much rare earth ore, but I think it's still yet to be discovered. There are some deposits, but so permanent magnet is used in, this is, you see that is helicopter, that's a windmill. And this is, in motors, you have large chunk of permanent magnet, and this windmill motor turbine will have permanent magnet bigger than a car size. Okay, so it needs a lot of permanent magnet, and they're expensive. So is hybrid cars, electric cars, they need permanent magnets in order to, you see here, so the motor capacity, right, in terms of HP, if you want high capacity, look at, this is, oh, I thought it was, sorry, ignore me. I thought it was, oh yeah. So induction motor versus permanent magnet motor. So this is normal induction motor. And when you optimize, do a lot of research in terms of finite element analysis and optimize, you get high efficiency induction motors. Induction motors use soft magnets, okay? So soft magnet motor, it has so much efficiency, the best one after all the research, whereas permanent magnet motor has so high efficiency because it has, it's just because how the motor is structured. Again, I teach that motor structure and how the torque is generated in a different class. But permanent magnet motors are much more efficient. So they are everywhere. And so permanent magnet motor for the same HP, induction motor is 45 kilos, permanent magnet motor is 18 kilo for 5 HP motor. Okay? So that's why permanent magnet motors are everywhere. And permanent magnets, are controlled by China. Okay. How many of you have driven electric cars? Yeah. So in electric car, you get instant torque, right? Just press the gas pedal. You don't call gas pedal, it's an acceleration pedal because there's no gas. So you press the pedal, immediately you have a torque. And so Tesla has much higher torque than other electric motors. So I drive one, and whenever in the beginning, it was 2020, 21, where I did not, just like normal car, I used to press, and after the traffic light, everybody is left behind. Initially I used to get, what happened? Was there some police stopping, or why is everybody behind? So it's unbelievably, you cruise fast at a small, it's not like you stamp the pedal. A little bit of acceleration takes you very far. So that is instantaneous torque for you. You don't have to burn anything, and the torque is really high because it has permanent magnet motors. And so I know it's time up. Oh, you have 2 minutes still. This is a 6-minute video. You get an idea of how permanent magnet is important for electric cars.
which in turn generates currents in the rotor bars.
So the induction motor, okay, this is Model S, the older model of Tesla. They have soft magnetic materials. Induction motors should have no coercivity. Otherwise, if you cycle the field to get induction or B, and if there is coercivity, is lost. Basically, the area in this curve is a lost energy if you cycle continuously. In permanent magnets, we don't cycle, but in soft ferromagnetic materials, if you magnetize and demagnetize them, then the area under the curve is lost as heat. So that means if you have higher coercivity, that you are going to generate a lot of heat. So those are, in induction motor, those are soft ferromagnetic materials. Okay, so
These small
I'll stop here. Tomorrow, uh, I'll start the first class with some applications of magnetic materials. Okay, so this is one permanent magnet we saw. I mean, permanent magnet motor application we saw. We'll look at magnetic memory and how we can use magnetic materials or magnetic concepts to measure residual stress or damages, micro cracks in any structure, steel pipes, and so on and so forth. Okay, any questions? Again, I should just talk less. Any questions? No? Are you all tired? Long day? Okay, so tomorrow come with some questions so you know now, right? So just out of curiosity, did anybody look at YouTube or about Parkinson's and deep brain stimulation? Yeah? DBS, I said go and look up on YouTube. I'm sure organizers are busy, but the students, I know you have a lot on your plates, but the students should, other students should have, you did, so you looked at how you turn on the DBS leads and suddenly the person becomes normal? Okay, so you have to do these kind of